Thank you very much. Can you hear me in the back? Yes? Thank you very much. Thank you, Nicolas, for that introduction. Thank you to the organizers for inviting me and allowing me to participate on this great school. I'm gonna try to do two calculations regarding supersymmetric Wilson loops in n equals 4. My idea is to first introduce what are Wilson loops, and then in the case of n equals 4 superunion mills, find the half BPS supersymmetric Wilson loop, which is a straight line or a circle. I'm going to try to convince you that it preserves half of the supersymmetries. And then once I do that, I will try to get the expectation value of that Wilson loop using ADS-CFT, holography. So that's the general aim of my 3 lectures, okay? So try to understand the half BPS Wilson loop from the gauge theory side, and then the holographic side, and then show that they match, okay? So now, in the process of doing that, I'll have to, I don't know at which level some of you are, so I don't know if most of you are undergrads, grad students, or whatever, but I will try to be self-consistent as best as I can, and introduce some basics of gauge theories and then some basics of string theory and along the way, okay? So let's say this is just an excuse to learn something new that is fun, and then that if you like, then you can go and read books and reviews and papers and delve deeper into this subject. So let me first start with a very motivation, I guess. So for the last 25 years, most of us have been earning our bread by studying what I call gauge gravity dualities. Okay, so this is a relatively old idea, back from the 80s, that says that if you have a gauge theory defined in some space, so this would be, let's say, 4-dimensional Minkowski space, you can describe that same theory with a gravitational theory that lives in one extra dimension. Okay, so this is the basic idea of holography. That's why it's called holography. So it's like a hologram. The gauge theory is like a hologram of the gravitational theory, right? So it's an old idea that goes back to Susskind and 't Hooft and people like that when they were talking about black holes and entropy, how much entropy you can put in a certain volume of space, etc. So now these were very loose ideas. There were some concrete connections, but they were loose ideas. But the main point is that this theory doesn't have gravitational degrees of freedom, while this one does have gravitational degrees of freedom. I'm not identifying which theory is which, okay, so for now it's just a sketch. So that's the first property. And the other important point is that the duality is what we call weak strong. Okay, so that means that when one theory is strongly coupled, the other theory is weakly coupled. So this is very important because this is the reason why we are interested in this duality, right? Because now we have two descriptions in principle of the same system, of the same physical system. We have two theories that describe it. And then in one formulation, the theory is weakly coupled and the other one is strongly coupled. So that's very useful. because it gives us a tool to study strongly coupled systems, which is something that is not very common in physics. So physicists, we mostly know how to do perturbation theory. And we're very good at it, actually. But doing nonlinear or non-perturbative physics is quite difficult. So this is a very useful and remarkable feature. So this means that when one system is strongly coupled, then the other one is weakly coupled. So in other words, when one system is very quantum, in the very far quantum regime, the other system is completely classical. And we know how to do classical physics quite well. So this is very useful. And then if you remember that one theory is a gravitational theory and the other theory is a gauge theory, you can, this is a big surprise because somehow Einstein's equations, which is the weakly coupled classical gravitational theory that we all know and love, we know how to do classical gravity quite well. Somehow, Einstein's equations know about Schrödinger's equation, or even its relativistic limit. They know, Einstein's equations know about quantum mechanics. That's something that, when you learn general relativity, you wouldn't expect. Right? There's no quantum mechanics anywhere. But gauge gravity dualities tell you that they actually know about each other. And the same is true the other way around. So if you study gauge theory using Schrödinger equation, you never see geometry emerging there. You never see a metric. You never see a space-time. But the equation does know about geometry and space-time and metrics and things like that. So it's a very deep insight that there's something about these two theories that we don't understand that makes them equal to each other. Okay? So that's the basic intro. Then, to be very precise, so these ideas were, in the collective mind of the community, but then they became really, really concrete, and it was like the big bang of holography when Mandacena in 1997 published this paper. I have here 18,248 citations. That's the number that's like a year and a half old. So let's say okay, this is 1997. And this was a very concrete proposal for holography that said that n equals 4 superbillion mils in d equals 4. So I'll explain what this theory is. Okay? Is the same as type 2B string theory on radius 5 cross S5. So again, this is n equals 4 superbillion mils would be this side of the duality. Type 2B string theory would be this side of the duality. So what is n equals 4 superbillion mils? I'll come back to this later. It's a gauge theory. It's a theory that isn't that much different from the standard model. So it has gluons and scalars and fermions and things like that. But it's defined on flat space, 4-dimensional flat space, and there's no gravity there. Okay, so it's the kind of theories that we more or less understand well. Okay, we in principle have a non-perturbative formulation of this theory in terms of the path integral and such. Now, it's a very, very special theory in the sense that it has a lot of supersymmetries and it's also superconformal, which is something I will come back to. But I just want to set the general framework. This is the quantum field theory in flat space. And then this is a string theory. Doesn't matter if you guys don't know string theory, but it's a theory of quantum gravity. Okay, many of you have heard that quantum gravity or string theory has to live in 10 dimensions. Okay, this is the 10-dimensional space-time. Okay, it's not flat space. So the background, the vacuum, is not flat space. It's a curved space, and it's a curved space composed of two products of 5-dimensional spaces. Everyone knows what a sphere is, so this is a 5-dimensional sphere. And this is like a cousin of the 5-dimensional sphere. It's called 5-dimensional anti-de Sitter space. So it's negative curvature, constant curvature space. Okay, we will see some details of this. But the point is that this theory now is a theory that contains gravitational degrees of freedom. If you go to the low energy limit here, this is type to be supergravity. Now, if you don't know what supergravity is gravity, supergravity is general relativity on steroids. So you take general relativity and you add more fields, you add some matter content, okay? And then that theory becomes what we call locally supersymmetric, okay? I think Breno is gonna, already did. This morning, no? Okay. Breno is gonna talk about supergravity. The point is that compared to the quantum version of string theory of Lola, supergravity is quite easy to manage. So it's just classical gravity, okay? Now, what about this weak, strong nature of the duality? So, if you have a theory of Yang-Mills, how many parameters do you have? Well, you have the Yang-Mills coupling, right? So it's the gauge coupling. That's one parameter. And then this also comes with a gauge group. In this case, I'm gonna, again, you can generalize this to other gauge groups. So you have SUN. You have gluons that live in gauge the D group SUN. And so then you have two parameters. So you have G Yang-Mills and you have N. Right? Those are the only two parameters of the theory. Why so few parameters? Because it's a very simple theory. Okay? If you had more complicated theory, you would have Yukawas, and you will have other gauge couplings for other gauge groups, etc. The masses of the fermions and all that stuff. So let me just erase this. What are the parameters here? Well, string theory also comes with a coupling constant. So now we have coupling constant G string. Okay, so this controls basically the same as the Feynman diagrams. It controls every time a string splits into two, okay, or two strings join into one, it controls the strength of that interaction. Just like Yang-Mills controls the strength of the Feynman diagrams. But then also, you have another parameter, which is basically the radius of the two spaces. So the sphere has a radius, right? And this space also has a radius. So it determines how much it curves. So a sphere with a big radius, we would say it's a small curvature, right? A sphere with a small radius is very curved. So the curvature is like 1 over L squared, 1 over R squared. It turns out that these two, in order for this to be a solution to gravity, they have the same radius. Now, so I could put here the radius as the second parameter, which is fine. Now the radius, you see these spaces have curvature, so there has to be something that's sourcing that curvature in gravity, right? Einstein's equations. And what's sourcing that curvature is what we call a Ramon flux. So technically, it's a phi form and blah, 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 but you can think of it as some electric field. Okay, for the purpose of this, just conceptually, it's some electric field, and that electric field, by Gauss's law, carries some electric charge. Okay, And that I'm going to call, so this is, I'm going to call n. So this is n, I just renamed this n sub c as in color, the number of colors that the theory has. And this is n, this is just the number of brains that source this electric field. Okay, so it's a stack of n brains. Again, it's not the point of this lecture to explain what d brains or p brains are. Just think of them as the same as electrodes and point charges. They source electric fields. Well, there's other fields whose sources are extended objects. Okay, so now you have these two parameters. Now, if these two theories are going to be the same, you have to relate them somehow. Okay, and then the dictionary says that D Young Mills is the same as G string, and that the number of colors is the number of brains. Let me check that exact. I think there's a 4 pi there that I. Right, squared and 4 pi. So this is G Young Mills squared. This is 4 pi G string. So that's the relation between the two theories. Okay? Now, usually in this side, we define what's called the 't Hooft coupling, which is G Young Mills squared times n, because this is really the parameter that controls the diagrammatic expansion. Okay? So you can think of G Young Mills as sort of appearing in your Feynman diagrams, but then each Feynman diagram will come with a trace or the gauge group, blah, 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 so there will always be a factor of n in front of the diagram. So lambda is actually a useful parameter to define in your theory. So let's say that we no longer say the parameters is G Young Mills, the new parameter is lambda. But of course, the important point is that there's only two of them. Okay? And the same thing here, instead of using G string and n, you can use the radius, which we find it. 4 pi G string n alpha prime squared. So this is 4 pi G string there's a factor of n, I forgot. Did I say that out loud? N. Okay. So alpha prime is just a constant that appears in the string action. It has units, so it's really not a fundamental new parameter, okay? It just sets the units for your theory. So now we have the radius of curvature that depends on GS and N, so I can get rid of either parameter in favor of the radius of curvature, okay? So now comes the neat part, which is the 't Hooft limit. So the 't Hooft limit is taking G Young Mills to 0, okay, and taking the number of colors to infinity. So this is just a limit, it's some limit in the parameter space of the gauge theory, okay? Why is this useful? Well, because it's the limit where we can say that the theory is classical, okay? So we will take these two go 1 to 0 going down 1 to infinity, but we will say that lambda is fixed. Okay? So we're taking this guy to 0, this guy to infinity, so many colors. Okay, so you're used to SU2 and SU3 in the standard model. This is SU 7185, right? But then we're taking a very weak coupling here. but then we're keeping lambda fixed. So the product of these two is fixed. Okay, so we're left with one parameter.
I'm sorry?
Yes?
The n on the string theory side, what was the explanation for that? Was the source for the curvature?
Yes, number of D3 brains that source the 5-form 1-on-1 flux. These are very complicated words, but the point is that if you want to have a geometry that is curved, you need a source, something that sources the curvature. Otherwise, there's no curvature. So in this case, what's sourcing the curvature is some type of generalized electromagnetic field, which is, it really doesn't matter the details at this point. Some sort of generalized electromagnetic field, and that has a stress energy tensor and curves the space-time. The electric field is sourced by some source. So electric fields in undergrad are sourced by point particles, right? Coulomb's law. Well, this 5-form is not a standard electric field. It's a different type of field, but it's sourced by extended objects, things that extend in 3 directions. And those are the famous D-branes. Well, I guess in this context they're called P-branes, but never mind. So these are the guys that source, and n is just how many of these you have. So it's like saying it's like having a let's say a charged sphere, and then you have to tell me how many electrons are in the charged sphere. In other words, you need to tell me the total electric charge, right? So Gauss's law. By Gauss's law, I can integrate the electric field. I get a number. If I divide that number by the electric charge of electrons, I get the number of electrons that are in the sphere. This is exactly the same. So this is the number of quote-unquote electrons. These are extended objects that are in the source energy. And the dictionary relates this number to this number. So going back to this is what we call the 't Hooft coupling, or the 't Hooft limit, sorry. And then I guess this is half of the 't Hooft limit, because then we take lambda to infinity. Okay? Now remember that the actual coupling of the theory, the coupling that controls the diagrammatic expansion, is lambda, it's not G Young Mills. So even though G Young Mills is going to 0, eventually we're taking lambda to infinity, so this is what we would call strongly coupled. Okay? This is what we call strong coupling. Now, what happens on the other side? So what happens on the string theory side when we take this limit? Well, what is this limit? Well, this means G Young Mills going to 0 is G string going to 0. Okay? That's nice. That means that all the string diagrams that we would take into account to compute our amplitudes in string theory are just 3-level. Okay, so we will just like in quantum field theory, these are just 3-level string amplitudes. Nice. And then the other part is n to infinity. So this would mean the number of D branes goes to infinity. But then we're taking lambda fixed. Okay? Now, if you notice, what is lambda in this language? So this is L to the 4th, right? N is the same as the number of colors. So I can just put N colors here. And then I got 4 pi G string, but 4 pi G string is G Young Mills squared. So this is exactly lambda. Does that make sense? So this means that L, so let's just write L to the 4th, just psychologically, because that's the combination that let's say L to the fourth over alpha prime squared. Remember, alpha prime is what sets the units in the theory, so it's not fundamental. This is fixed. Okay? And then we take L to infinity. So that would be the same limit on one side, and then that same limit on the other side. Now what does this mean? Well, if I take the coupling constant to 0, that means I'm doing sort of classical string theory, right? I'm just keeping my tree-level string diagrams, which is nice. So this would be sort of like a classical limit. Okay? But then I'm keeping the radius of curvature of this space fixed. So I'm doing classical string theory on this background. But then the second part of the limit, when I take the radius to infinity, what happens? Well, if the sphere is not very curved, if the sphere is quite big, and I put a string on top of that sphere, how does the size of the string compare to the size of the sphere? Well, the string is going to be very small, right? It's going to look like a point. Does that make sense? And the same on ADS, of course. So if this space is very big in the sense that the curvature is not that big, the string is going to look like a point. And what is the point-like limit of string theory? Classical gravity. This is just supergravity, okay? So then this means that this is, so here strings become points. So they're no longer described by strings, and then we know that in that limit, this is just classical. Supergravity. Okay? So this is the nice corner of ADS-CFT, right? So this is the limit in which we know how to do things. This is easy. Okay? The opposite limit, let's say when the string theory is very, very, very quantum, we don't know how to do that. Okay? We know how to do that on flat space, on shell. So that's all the string theory books that you would read are that. But we don't know how to do string theory in ADS 5+5. Maybe Osvaldo knows at this point, knows the vertex operators of this. But it's very hard. So doing proper full quantum string theory in this background is very, very hard. So this limit is far away from that. But the other way around, when this is very quantum and strongly coupled, this one is weakly coupled. And we can use perturbation theory on gauge theory, which we know how to do. So you in principle could learn something about quantum gravity doing weakly coupled semi-classical quantum field theory. Okay? Now that avenue is not explored that much usually. Usually we go the other way around, because by doing weakly coupled classical gravity, we can learn about strongly coupled gauge theories. Okay, so this is where the interesting physics happens in the lab. So this, if we are lucky, someday this side will be the standard model, or this side could be a superconductor, or this side could be a vial semi-metal, or whatever field theory describes physics in the lab. And then the other side will be some complicated version of string theory, but it'll be classical, right? So this is the main motivation for us at this point, okay? Now, so let me now move on to Wilson loops. So you want to learn something about each side by studying something that is well known here, and then trying to describe it here. And then, if you're lucky, you learn something about this theory here. So that's our motivation for Wilson loops. Okay? So usually, one would one would look at different observables in the Gates theory, observables that are interesting because of collider physics or whatever, and you would try to describe them here and then try to learn about this type. Or the other way around, some interesting observable here, let's say black hole entropy, for example. You want to understand the microscopic origin of black hole entropy, and then you can try to map that problem into a problem here and try to learn about both sides. Okay, so that's the idea of gauge gravity gauss. Now I'm talking more in general, not these two specific theories, which is the example that I'm going to focus, but more general. So here you would usually study correlation functions. Okay, of local operators. My handwriting gets worse and worse. Wait a minute. So that's one. I'm not going to focus on these. These are, in most reviews about ADS-CFT, this is where they start. They begin by giving you a prescription of how to compute correlation functions in the CFT using classical gravity. Okay? And then you study the ADS space and the asymptotic solution of scalar fields and vector fields, etc. That's very important because correlation functions are the building blocks for whatever observable you want to compute in your Gates theory, right? But there's another family of operators which are called Wilson loops, and they're non-local. Okay, and they also give you important, relevant information of the Gates theory. Actually, you could, in principle, reformulate the whole theory in terms of Wilson loops. Okay, that was the original motivation. But let's just, for the moment, say that, look, if I want to study local properties of the quantum field theory, I would study correlation functions with local operators, maybe some global theory, some global aspects of the theory, I could study Wilson loops. Okay, so these are the two main observables that one would like to address or one would like to study in a Gates theory. There's infinitely many more, of course. Let's say if this is a superconductor, you want to compute the conductivity or whatever other observable you might want to compute. What I'm saying is that those other observables usually are written in terms of building blocks that are these two types. Okay? I left out black hole entropy because this is just in Gates theory, but in gravity there's also observables that you might use. So today I'm going to focus on this. I'm going to try to explain from this perspective what these guys are, and then hopefully in the next two lectures I will describe them in this context. Okay, so then you can get a general overview of how the duality works here. So, what are Wilson loops? Here I'm going to assume that you guys already know more or less what a Gates theory is, and I'll just remind you of a few ingredients, but I don't have time to go over all the ingredients. But what is a Wilson loop? So there's two ways, well, more than two, but two standard ways to sort of motivate the definition of a Wilson loop. The more physical one, which is the second one you wrote here, that's why I'm. Where is this? So the first is, imagine, let's go to electrodynamics, okay? This is Jackson, oh, not Jackson, let's Byrne, actually. Let's normalize, Jackson is not a good book, okay? But some advanced electrodynamics book. Let's say you have some electric field, okay? E and B, in space, some background fields, I'm not saying who's sourcing this, and then I put a probe particle. Okay? So probe particle in this background that of course feels the electric force and the magnetic force. Okay? So the Lorentz force. And then I ask myself, what happens to the weight function of this particle when I move the particle from point A to point B, let's say. Okay? Okay, so if I go to A to point B, right? Or actually, yes. What happens to that particle? Well, the wave function acquires a phase. Okay, and that phase is equal to the action of the particle along the path on which it moved. Okay, so this is just standard quantum mechanics. This is easier to understand if you go on a closed loop. So you take the particle, you go for a picnic or whatever, and then you come back to the same point. Because it's the same point in space-time, the wave function should be the same, right? Except that you learn in quantum mechanics that two wave functions that differ by a phase are the same physics. So it could be that this wave function did not return to the same value, but returns to the same value up to a global phase. So that's the idea that I'm trying to use. Okay, now that global phase will be the action of the particle along this path. Okay? So this will be, so let me just, let's do a closed loop then. So the wave function started at A and then went back to A, and this will be e to the I, the action of the particle from A to A, I should say. Okay, B is just an artifact here. Okay, good. Now, the action has two terms. The Lagrangian has two terms. It has a kinetic energy and has a potential energy, right? What happens when the particle, this is a probe particle, so this is not the particle that's sourcing this electromagnetic field, okay? So there's no back reaction here. But what happens when the particle becomes very, very heavy? If the particle becomes very, very heavy, then the kinetic term is negligible. P squared over 2m. Right? The classical kinetic energy. So if the probe is very heavy, the kinetic energy does not contribute. This is not, by the way, this is not a classical path. This is not following Euler Lagrange equation. This is what some books call the virtual path or whatever. I hate those terms, but this is just the path that with my hand I pushed this particle through the electromagnetic field and I moved it wherever I want. So this is not just a free. It's not a particle that's moving along the solution to the equation. So this is me dragging this particle. So if this particle is very, very heavy, I'm going to have trouble dragging it, and most of the energy will be due to the potential energy along the path. Well, what is the potential energy of this particle then? Let's just think of non-relativistic classical particle. What's the action? What's the Lagrangian? Well, it has the kinetic term, which I'm neglecting, and then the potential energy, how do you write it?
It will be
Yes, so it's the charge times the electric potential, right? There's a covariant version of that, which is the integral along the word line of A mu x dot mu. See, if you go to the frame or you use coordinates where the proper time is the same as the space-time coordinate t, the first component will be 1, right? So t dot will be equal to 1. And then this would just be a t or a0, which is the electric potential, right? So this is right? And then the other part will be v, the velocity of the particle, cross, or I would say dot a, right? Which when you vary, and you must have done this exercise, gives you the Lorentz force. Gives you the v cross b term, right? Because remember that b is the curl of a, so there'll be some cross product will appear there. So the point I'm saying is that this is what captures the potential energy of the probe particle. And that's exactly how we define the Wilson loop. So this motivates around some closed path C. So everything I said was just motivation. We saw that this quantity controls somehow the effective action of this particle as we go around the loop, of a very heavy particle, as we go around, which is what we call a probe, a very heavy particle. So we'll just give it a name. That'll be called the Wilson loop. Okay? I will do this again in a more formal way and in non-abelian theories as well. But this is just the physical motivation. Okay? I'm sure you've seen this formula in many places. So I will give more details when I do it properly. Okay? This is just the motivation. Two things. What does this operator, this new quantity W, depend on? Well, it depends on the path C, right? So this is a path in Minkowski space. It's closed. And of course, if I want to compute this quantity, I need to say which path that is. Okay? It's free. I can choose whatever I want. Why choose one or the other? Well, what do you want to compute? What information do you want to extract from the theory? Then you choose one path or the other. For example, if you choose a path that shrinks to 0, you would be computing local operators, right? So it's a path that shrinks to a point. Somehow you would be recovering the local formulation of the theory. But it also depends on what else? So I neglected a detail there in the action, which is
sources. You said there wasn't sources. So.
The source for electromagnetic field. Now those are regarding as background at this point. Okay. What if the particle doesn't have any charge? Do I need to do any work to move it around? No. So its action, the effective action would be 0. So actually, there's a Q in front, right? Of course, the electric energy is Q times phi, not phi. Okay, so there's a Q here. And also, so this depends on the charge Q. Okay? So I have two parameters or degrees of freedom, if you want, that I can play with. I could put a probe that is very whose charge is very small or whose charge is very big, and I can play around with the path. Okay? Now Q cannot be infinitely large, because then precisely the fact that I'm neglecting that this guy is also sourcing some electric field, I neglected that, right? So the sources are somewhere here hidden, right? This creates EMP. Now Q is very, very large, then there will be a back reaction. Q will create its own EMP. So Q cannot be very, very large either. Okay? So this is the physical motivation. Let's do something more formal. So now we'll do it in non-abelian theories, and the physical interpretation will be exactly the same, right? So we will be computing the effective action of some prompt particle in this theory, but so in Yang-Mills, the gauge field is, what's the right word in here? Lives on a Lie algebra, right? So the example we have in mind this whole time is SUN. Actually SU2 if you want, just to make things very concrete. Okay? So this means, for example, in the case of SU2, that my gauge field is now a matrix, a 2 by 2 matrix. Okay? And there's 3 of them, because the SU2 Lie algebra has 3 generators, right? This is the Pauli matrices if you want. So there's one gauge field associated with sigma 1, another gauge field with sigma 2, and another gauge field with sigma 3. Each of these are vectors. I'm not saying these are the components of the vectors. Each of these 3 are vectors, right? So we usually write this as A mu is A mu A TA, okay? Where TA are generators of the algebra, and the index A, of course, goes from 1 to the dimension of the, let's say, I'm not going to give it a name, it's not that important. So in the case of SU2, this index A would be go from 1 to 3, right? Because there's J, this is quantum mechanics, right? X, Y, and Z. There's 3. In SUN, how many generators are there? N squared minus 1, right? So that's why you have 8 gluons, right? 3 squared, 9 minus 1 is 8. So now I'm going to think of the gauge field not as just one field, but I'm going to think of it as a matrix of fields, okay? And this matrix is going to be expanded in some basis of the Lie algebra, which we call generators, in this manner, right? Now, I will also use the notation A as A mu dx mu. So I will hide also sometimes the index mu, just for convenience. So for example, SU2, you would have T1 would be 1/2 of 0, 1, 1, 0. T2 would be 1/2 of 0 minus I, 0. And T3 would be 1/2, 1, 0, 0, minus 1. Okay? And then you would have 3 gauge fields, 1 for each matrix. Now it's important that this is actually one representation of SU2. Okay? This is what we call the fundamental representation, which in the case of SU2 are 2 by 2 matrices, but in the case of SUN are n by n matrices. So in the case of SU3, so in SU2 these are the Pauli matrices. In the case of SU3 they are the Gelman matrices you can find in Wikipedia. So there's 8 of them. Okay. But there are infinitely many others. And these you know from your quantum mechanics course. So you go to GravUC or whatever quantum mechanics books you like. These are the famous J, L representations of SU3, right? So if you put J equal to 0, these become 1 by 1 matrices, which are valued equal to 0. If J is equal to 1/2, you get exactly this. If J is equal to 1, you get the spin 1 representation, which are 3 by 3 matrices. Okay, and so forth. So you can grow the size of the matrices 1 by 1. But the point is that whichever representation you choose, they will always satisfy that. So the 2 by 2 matrices satisfy that. The 3 by 3 matrices satisfy that same algebra, and so forth. That's the whole point of a representation, right? So you change the size of the matrices, but you don't change how many of them there are, and you don't change their commutation relations. Okay? Good. So why am I mentioning this fact about representations? Because now that we're in the non-abelian case, what is the charge of a particle in a Yang-Mills theory? So let me make this more concrete. Let's say you take a complex scalar field. This is the usual way they introduce the gauge field A mu. So start with a complex scalar field, d mu phi, let's put mass equal to 0, whatever. And you notice that that has a global symmetry where you change the phase of the field. Nice. And then you say, for some reason, I want to make this symmetry local. So I want to put alpha as a function of space-time. You realize that doesn't work, but you can actually make it work by introducing a new field, right? Which is called A mu. And then you write some covariant derivative and blah, blah, blah. And then that works, right? But there's a free parameter, which is the number that goes in front of the A mu in the covariant derivative. Remember that? Which is also a free parameter that goes in front of the parameter of the phase in the gauge number. So I have a freedom to do that. If I set that parameter equal to 0, I say the field is not charged, right? And then I can set the parameter to whatever value I want, and I call that the electric charge. Now, why do I call that the electric charge? You can compute the netted current associated to the global symmetry, and you compute it, and that's proportional to Q, right? Or the whatever parameter. Okay, nice. What about now if I do Yang-Mills? So let's say instead of taking one scalar field, I take 2 scalar fields. Okay, now I can write a Lagrangian that is invariant under SU2, right? Perfect. I want to make it local. I already know the trick. Introduce a compensator gauge field that now has to be a 2x2 matrix, etc., etc. There's no longer a charge there. I don't have the freedom. Well, I can still put a number that's called the Young-Mills coupling. But let's say I do it for a doublet and a triplet at the same time. How do I distinguish the doublet from the triplet? What makes them different? Well, the size of the matrix that is acting on them. So in one case, if I'm acting on the doublet, the gauge field in the covariant derivative will be a 2x2 matrix. But if I'm acting on the triplet, the gauge field on the covariant derivative will be a 3x3 matrix. Right? So the gauge field knows what size matrix it has to be because it knows who it's acting on. So how do I, but there's no free parameter there, you see? Well, there's one free parameter, I guess, the G Young-Mills parameter in front of the covariant derivative. But then there's no charge, what we call the charge. So what plays the role of a charge here? The representation. Does that make sense? So in non-abelian theories, the representation of the gauge group plays the role of charge. So if this idea is not clear, just think of, let's say, go back to the abelian case where you have two U1s. You have only electromagnetic fields. And then now say you have two particles and they have different charge. So you can introduce a Young-Mills coupling in the covariant derivative on both. That's fine. But then what distinguishes one particle from the other is what goes next to the G Young-Mills coupling, right? That will be different if the charge is 0, 1, 3, 1/3, or whatever. This is in the standard model. So this is, when you go to the non-abelian case, the same thing happens. You can put a G Young-Mills coupling in front of the gauge field in all of the covariant derivatives, but what distinguishes one particle from the other is the size of the gauge field, how big it is, okay? In U1, all representations are labeled by a single number, which is Q. So that's why they never explain this to you in this language. But when you go to the non-abelian case, the representations now change in size, so you need to make this little switch. So that's the message here, right? So you have the representation of the gauge group. And then the covariant derivative is, so we all know this d mu, it'll be the partial derivative minus I, and here I'm going to write G Young-Mills A mu. Okay? What I was just saying is that there's another parameter here which is hidden, which is the size of the matrix. Okay? And that plays the role of the charge. Right? This just plays the role of how strong the coupling is. Right? But this is the same for all particles. Right? And this distinguishes from particle to particle. Right? And this you already know from the standard model. Okay, you've seen it. This is what we call the singlet of SU2 or triplet of SU3 or whatever, right? This is just saying what representation you're setting there. Good. So this has the nice property that it transforms covariantly, right? So under gauge transformation, write this nicely. You will have a new connection. Hopefully I got the coefficients right. Okay, so over G, let's say, I'm going to just think of SUN completely. It could be any Lie algebra you want. Okay? And also, we write G as e to the I t, where t is some combination of my generators in the algebra. Okay? Let me just call it alpha. Usually you call it in U1, right? Or lambda. The point is that this guy lives in the algebra, this guy lives in the group, but they're both matrices. So this is a matrix exponential. Okay, so, this is, of course, I'm doing things very, very fast. But the nice thing about this is that if I have a field that transforms like this, which is what we call a matter field in the representation, whatever representation I'm using here to describe this G, then d prime of phi prime is d phi prime, and this will be just G d phi. So this is the standard phrase that the derivative transforms exactly the same as the field. Okay, so this is something that you already know. So this, if phi transforms nicely, then d phi also transforms nicely, right? You want to really add the index mu here so that you don't get confused, right? Good. And then the other ingredient is what we call the curvature. This is dA plus A wedge A. Okay, now I'm using differential forms. If you don't like this, I can write F mu nu is d mu A mu minus d mu A mu plus the commutator of A mu and A mu. So remember, these guys are matrices now. Okay. And this guy transforms nicely. So this F prime is equal to G F G minus 1. So this is what we would call the covariant transformation. You see, vectors, quote unquote, transform like this. But if you have a tensor, one side will transform with a G and the other index will transform with a G minus 1 because it's on the other side, right? So this is the same as GR, right? When you have a two-index tensor, there's one Jacobian for each index that you need to add. If the index is upstairs, you get the inverse Jacobian. So this is exactly the same, all right? All right, so now these are the basic ingredients. How do we define the Wilson line here? Okay. So take some path. Okay. X dot mu, some line in space-time, and solve the geodesic equation for this connection, right?
Sorry. The commutator appears now because we're working in SUN rather
Yes.
than
So if this is a billion, this is 0, and you get the usual thing. But in the non-abelian case, you get a commutator, right? And I'm sure I'm missing a factor of G and Mills here, but I don't want to write it because I'm not sure if it's. I think it's 1 over G and Mills squared, but I could be wrong. You can check that in your book. You can always reabsorb it in AMU. So take let's say so let's try to study that equation. This is if this was GR and phi was a vector and D was the covariant derivative with the Christoffel symbols, this would be the geodesic equation. All right? Where, I'm sorry, this would be the parallel transport equation of that vector. Right? And then if phi was x dot mu, that would be the geodesic equation, right? So this would be called parallel. You want to write it? Parallel, 2 L's, 1 L?
one being the same.
No?
No, that's not.
So let's write it in Spanish. This would be parallel transport. So let's try to solve this. So this is the same as ds of phi equals I a mu x dot mu times phi. Okay? Where, of course, dds is x mu dot d mu. So it's the tangent derivative along the curve, right? It's just a chain rule. So this would be the equation. And, sorry, I forgot, I wrote a G in Mills there, sorry. There's a G in Mills. Right. So all I did was take the connection part, moved it to the right side, because this looks like an exponential equation, right? The derivative of phi is equal to phi. So the solution must be an exponential. It's a little bit more complicated now because these are matrices and the coefficients here are not constant. So if this was constant, this would just be an exponential, no problem. So let's do the first thing that we can do, which is try to solve this perturbator. All right? We'll get a surprise. We can actually solve it exactly using perturbation theory, but let's try that. So let's do a perturbation in G and Mills. Okay, so I will write phi as some phi 0 plus G and Mills phi 1 plus G and Mills squared phi 2 plus dot dot dot, right? I'm going to try some series solution in G and Mills, which is my coupling constant, and try to solve it. Well, if I plug this ansatz here, I will get a recursion relation, right? Because this is order 0 in G and Mills, this is order 1. So the equation would relate one order with the previous one. Okay, good. So this would be ds of phi 0 plus G young males phi 1 plus dot 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 equals to I G young males x dot mu a mu times phi 0 plus G young males phi 1 plus dot dot dot. Right? Now I just equate order by order in G young males. So the first one will be d ds of phi 0 is 0, because this is the first one ordered G young males to the 0, and this one starts at G young males. Right? So at first order, phi has to be constant. Nice. What about the next order? 10 minutes? So next order, I will have d ds of phi 1, right? So it'll be this term. And I need to, what is the order 1 term on the other side? Well, it's phi 0. So this will be I x dot mu and mu phi 0. Okay? And then obviously I will get d ds phi n is equal to I x mu dot a mu phi n minus 1. Right? That's the recursion relation. Well, can we solve the first one? Can we get phi 1? Actually, we can, formally. So we can write phi 1 less as I times the integral from 0 to s ds prime x dot mu prime well, actually just look like times phi 0. You guys agree? Because we already know that phi 0 is constant, right? So if this is constant, then all I just do is integrate this part, and then that is a matrix. It hits phi 0, and that's the solution. Of course, here I chose that phi 1 at 0 is 0, but that's just a choice. Okay, I'm giving all the initial conditions to phi 0. Okay, it's just a choice. Okay, if you guys wanted to put some other limit here, I don't care. This is just the standard integration constant you get when you solve for first order differential equations. Okay, so this was just a choice that I made. Well, what about the next one? The next one will look very similar. Okay? All I have to do is take this solution and plug it into the next equation, and then try to integrate. Okay? Again, this is a formal solution. Okay? This is not a. This will be I integral from 0 to s ds prime x dot mu a mu. Now I have to put phi 1 here. Right? Because phi 1 is not constant. So when I integrate this, now the integral, this guy will have to be inside of the integral. Right? But I know what phi 1 looks like. There's an integral and then there's a constant part, which is phi 0. So if I plug this in, I will get I integral from 0 to s ds prime x dot mu a mu. And now I'm going to distinguish, I'm going to be more careful. I'm going to put a prime here and a prime here, meaning that those two functions are evaluated at s prime. Okay? So this part would be this, and then phi 1, but phi 1 is itself an integral. So this will be an integral from 0 to where? Where is phi 1 evaluated in this integral? Phi 1 is at s prime, right? So that means that this upper limit has to be s prime now. So from 0 to s prime, and then I need to relabel the integration variable, ds double prime, x dot mu double prime, a mu double prime, and I forgot an I there, and then all of this times phi 0, which is constant, so I moved out of it. Okay? And then, now here comes the trick. You can see how this is going to be when I go to third order, fourth order, blah, blah, blah. I will get these nested integrals, right? Now you can see that happening clearly. And there will be factors of I to some power. Those are easy to keep track of. But the trick now is to write this as, well, I'm going to just write this as I squared. So it's minus 1, but just so we can generalize to two other cases. I'm going to write this as the integral from 0 to s in ds prime, the integral from 0 to s prime, ds delta prime. I'm sorry. So I'm going to keep here s, and then see this integral here is up to s prime, not s. So I need to do something different here. And the trick is that I write this as, so let me just, I squared this as 1/2 of the integral from 0 to s, integral 0 to s, but then here I write the something that I'm going to call the path order operator. I'll say in a moment what this means. Of x dot prime mu a mu prime x dot double prime nu. See, this should have been smaller index. A dot prime nu. Okay, this where the path order means whichever function is evaluated earlier in the path goes on the right. Okay, and the later value of the parameter goes on the left. Right? So if you take a moment, forget this integral for now. This is from 0 to s. Okay? If you split this from 0 to s prime, and then from s prime to s, right? You will have the two orders appearing, right? So if the integral from 0 to s, then, from 0 to s prime, then s double prime is smaller than s prime. Right? The integration variable is always smaller than the upper limit. So in that case, this is I can just remove that because the earlier time, or the earlier value of the parameter is double, S double prime. So that would go on the right, this would go on the left. But then on the other half of the integral from S prime to S, right? S double prime will be bigger than S prime. The variable is always bigger than the lower limit. So then you would flip these two. Okay? And you can convince yourselves that this is the same as this. Because it's just a relabeling of who is S and S prime. Or who is S prime and S double prime. So then you separate this into two, use the path order, and then you change the name of the integration variables. And you will get the same contribution from both integrals. Does that make sense? More or less? All right, sit down. It'll take you 2 minutes just to realize this. So again, I repeat on the other part, now the order will be reversed. So this guy will appear in the left, this guy will appear in the right, but then I relabel things. What S prime becomes S double prime becomes S prime, and you get exactly the same integral as before, and therefore cancels the factor of 1/2. Okay, that's the idea. Good.
When you split the integral, there's going to be an integral that goes from S prime to S and not from 0 to S prime. Isn't that a problem?
Yes, it is. I mean, no, it's a problem for me right now because I don't remember what happens, but it's not a problem. Just let me look at it more carefully. So, so you're saying when I split the integral, I get the integral from S prime to S. That's true. Why is it not working? All right, let me finish. I can sit down and do it more carefully. But it's a question. Anyways, the point is that now this is easily generalizable to so the general solution will be the nth term will be I to the n over n factorial, and then you will get a multiple integral you get n integrals of the path order product of A in S1, A in Sn, where I abbreviated A as x dot mu in mu. Okay, but it's the same. It's just that that thing is evaluated in S prime, this in S double prime. I just call this A, right? And now I forgot about the primes because I relabeled them 1, 2 through n, and this combination is called A. Okay? And this times of course 5, 0. And then if you notice, this is the series of the exponential function. Right? So therefore, my solution will be the path ordered exponential of e to the I integral from 0 to s of a mu x dot mu ds, and I will have GN mils there. Okay, does that make sense? Now all I have to do is add all the phi n's times powers of GN mils. That was my original ansatz. I recognize that this guy will factor out. Phi 0 will factor out. And then I will get a series that I can easily recognize as the exponential series. So I write it like this. Now, it's a sort of a circular definition. So the meaning of this object, p e to the I, blah, blah, is precisely this series extension. Right? To give it proper meaning, you need to. So let's say this is just a shorthand for the sum over all n. Okay? So I'm going to leave it at that for now. And now you can see this is my Wilson loop. Okay? So I gave you another reason why we should look at these kinds of operators. So the physical reason is that this is capturing the effective action of some probe particle that couples to the gauge field. All right? It captures the effective action of this particle. And then the other one is a mathematical artifact where, not artifact, but has the more geometric mathematical interpretation of a parallel transport along the curve. All right? So, thank you very much.